Hello guys, welcome back. So here is another question from GATE EE 2022 based on network theory. So the network shown below has a resonant frequency of 150 kHz and a bandwidth of 600 Hz. The Q factor of the network is dash, round off to nearest integer. So here is the network they have given. So they're asking for the Q factor. So what is the Q factor? So Q factor is nothing but your quality factor. And the quality factor itself has many definitions, but in this context, if you see, they have given bandwidth. So bandwidth means this circuit is used as a filter and it has some particular bandwidth to select some that range of frequency, right? To select a frequency range. And what you mean by quality factor? When will a selective filter have higher quality? If it is having lesser bandwidth. If it can fine tune to that just that particular bandwidth and select only that frequency, then it is good, right? So for example, if I take a case of a band pass filter, let's say it is positioned at omega naught, and my first filter is something like this, and my second filter, let's say, is something like this, and my third filter, let's say, is something like this. So if you observe, this red color line has high selectivity. Why it has high selectivity? Whatever is outside this bandwidth, it rejects. So we are only interested in the signal at omega naught. So it is good for us to have something like the red color. So this is always better or good for us. So then ideally this should have a higher quality factor. So if you see the definition and the formula, the Q factor is nothing but it is the ratio of your resonant frequency to your bandwidth. So if I take this as delta omega, my bandwidth will be 2 delta omega. So it is ratio of resonant frequency to my bandwidth. So at least you know that it is inversely proportional to my bandwidth and you need some reference. So just by bandwidth can you say that it is okay? For example, if your signal is at 1 gig and you have 100 megahertz bandwidth, this case to compare it to the signal of I have it at 100 megahertz my resonant frequency and I have 100 megahertz bandwidth. Definitely this case is worse, right? Although both have same bandwidth, the second case is going to be worse. So you need some reference to start with when to compare the bandwidth. That is why we have omega naught, the resonant frequency, as the reference. So higher the resonant frequency, for the same bandwidth, you will have higher quality factor. That is why if you see the mobile networks they are moving towards the higher band, right? For example, if let's say you have 3 mobile towers and each wants to send the data of let's say 10 megahertz. Now if their resonant frequency is located around let's say 50 megahertz, then let's say in and around this 10 megahertz means they almost occupy the band, right? But the same thing if let's say it is at 1 gig, so they will only occupy a very tiny band. So you have a lot more space to play with as you move towards the higher frequency. So that is why this omega naught by 2 delta omega is important for quality factor. So now this is directly the formula substitution only. So Q is equal to omega naught is 150 kilohertz here divided by 600 hertz. So it is 0.6k. So it is 1500 by 6. So 500 is 250. So my quality factor of the network is 250. So this is in the context of your filter. But if you just have a RLC network and you want to find a quality factor of that, there the definition is at a resonance, quality factor is equal to your ratio of energy stored. So energy stored in L or C divided by energy dissipated. So what is the dissipating element here? R. Dissipated in one cycle. So that is why if you have a series RLC, at resonance your energy dissipated will be, here your I is constant, right? So your Q will be I square XL, let's say that is the energy stored in L divided by I square R. So this energy stored is across one element only, either L or C. Okay, so it will be XL by R, which will be my omega naught L by R. XL is nothing but J omega naught L. and this is at resonance, so omega we have to substitute as omega naught. Okay, similarly you can calculate it for the parallel RLC circuit, and in that case what you will take, the voltage is same, right? So you will get V square by XL and V square by R. So for parallel you will actually get inverse of this, R by omega naught L, and again this omega naught is related to LNC as 1 by root LC, so you can substitute it here to get in terms of R, L and C excluding omega naught. Okay, so this is easy to remember only if you remember the circuit and the concept. Okay.